In section 6.2, we're going to learn about inverse functions. The first part of this is really just review, getting some properties of inverse functions, how they look, what their behaviors are. Then we're going to start taking derivatives of inverse functions. It's really not a hard section. I think you guys will be okay with it, but we do need to learn some things about it. Firstly, what does it take for a function to have an inverse?
X and a Y.
It's got to have an x and a y, right. But it's got to be in a relationship that's very specific.
1-to-1?
That's right. It's got to be one. Have you ever heard that term one-to-one before? One-to-one means that in a function, every input has one unique output. That means if you plug in a number and you get out 2, you get out 2 once, you never get out again. In other words, I can show this with the horizontal line test. You ever familiar with the horizontal line test? One of these functions is one-to-one, one of them is not. Which one's one-to-one, left or right? That's one-to-one, this is not. The horizontal line test passes here, it fails here. This says that you have multiple outputs of the same value. That would fail being one-to-one. That matters for inverses, because in inverses you switch x and y. If you switch x and y, inputs become outputs, outputs become inputs. Let me explain why that's important. If you have a non-one-to-one function here, and you try to find an inverse, it's going to go like this. It's not even going to be a function anymore, and that's a problem. So what we say is that for a one-to-one function, we can find an inverse. For a one-to-one function, f of x, it's absolutely true that if a function is one-to-one, it will have an inverse. So for a one-to-one function f of x, an inverse, it's denoted f, you've seen this before, I'm sure, f inverse. It's not f to the little -1, okay, it's not how we say that. It's not an exponent at all. It's probably the worst notation in all of mathematics. I don't know why they have the -1 there. It does look like an exponent, but it's not one. It's pronounced f inverse of x. So for a one-to-one function f of x, an inverse f inverse of x can be found. Little side note here. This is how you check whether two functions are inverses. It's just a little simple composition. If you do a composition of f inverse onto f or f onto f inverse, what an inverse does is it undoes a function. And a function undoes its inverse. I always say it's like a... Any of you guys have kids? Nobody? Oh, you do? Okay. So it's like a little rotten kid, all right? So they're not rotten though, are they? Okay, good. Well, if I have kids, they're probably going to be rotten kids. So it's like if you went around cleaning your house and the kid right behind you went, "No! No!" and put everything right back to where it went. So they have their toys all messy, you pick up a toy, they go, "No!" and they put it right back. Okay, that's what inverses do. They undo everything that you just did. So if I plug in x into my inverse, it's going to do something. F is going to clean it up, put it right back where it was. Or vice versa, f would do something, and inverse puts it right back where it was. What that means is that whatever I plug in, it's going to go through the machine, go through the anti-machine, and give you back exactly what you plugged in. That means that if you compose two functions that are inverses, your result will be x. And that's either way that you go here. And that's how you check. Let me give you an example on how you find inverses, then we'll check it with the composition to show that I'm right here, that I'm giving you the right thing, and then we'll talk about the graphs, and we'll probably end it right there. So, let's find an inverse. First thing I want to tell you, it is one-to-one. Next thing, let's find an inverse. Here's how you do that. Ultimately, our goal on inverses is to switch the x and the y. That's what inverses do. To do that, we have to have a y. So typically what people will do is they'll change whatever the function name is into y. So instead of f of x, we're going to have y equals your function. Next thing, here's the place where you actually make the inverse. Everywhere you see a y, you put an x. Everywhere you see an x, you put a y. You just change the variables here. So what's that going to become?
X.
And what's this going to look like? 1 over, very good. And?
Square root of 2y minus 3.
Yep, that's right. You okay with that so far? The idea now is you have to solve for y. Just solve for y. Give me some ideas on how to solve for y.
Replace the bottom denominator with x.
Sure,
Switch them.
we can just switch those.
Move the square root over
Or
or
both
square
sides.
both sides.
And then add 3.
Cool, we can do that. Well, that's 2y minus 3 equals 1 over x squared. Absolutely. All right. Then what'd you say?
Add 3.
Cool, we can do that. So 2y, if we add 3, is this.
Divide by 2.
Yeah. If my math is right. Did you guys get the same thing? Just for funsies, let's make this one fraction. So if we made it one fraction,
1 over x squared plus 3.
1 over, we'd have to find a common denominator that would give us 3x squared over 2x squared. So we'd have 1 plus 3x squared over 2x squared. You guys okay with that one? At this point, you found your inverse, just call it the inverse. So the notation we use, if we start with f, we're going to have f inverse. If we start with g, we're going to have g inverse. All you do is you put whatever the function name is, the inverse notation, and then rewrite it. Quick head nod if you're okay with that one. It's really not calculus, we're just doing some inverse because we're going to be doing some calculus with inverse later. What I do want to show you is that if you do compose f inverse with f of x, and this is either way you want to go, you can do f inverse here and f of x, it doesn't matter, you're going to get x in either case. Here's what this would say. It says, what I want you to do, I want you to take this function, I want you to put it everywhere you see x here, and see what you get. That could be the easiest one. Oh man, either way it's going to suck. That would be our composition. Are you guys okay with the composition? You see where everything's coming from? We're taking f of x, we're putting it into our inverse function, and we're checking to see that we've done all our work right. We're checking to make sure that these are actually inverses. Do you see what I'm talking about? So we have 1, sure, plus 3, no problem. This x becomes that function. That's what we got. This x becomes that function, and that's what we got. So if we continue with this, I'm going to have to move over here. Tell me what the squares do. I know it's fast, but I wanted to prove it really quick because we're out of time. we just proved that those things are actually inverses. Just do a little bit of algebra. It says anytime you compose two functions and you actually get x out of it, then you know they're inverses. Could you follow that one?
Yeah.
Did I get too fast with that one? A little bit? Do you have questions on it? We have about 10 seconds.
So pretty much just to prove yourself, you plug in whatever
Yeah.
f x is. Whatever.
Yeah, you compose them, and if your answer is x, you know they're inverses. All right, so we're right at the beginning of talking about inverses. I remember last time that we actually found the inverse of one function. The idea behind our inverses is basically this. For every one-to-one function, you can find an inverse, which is also one-to-one. We'll talk about a couple properties right now of inverses. I'll give you some examples on how to use this as far as calculus goes. Then we'll start talking about another topic. So, a few notes on the relationship between a function and its inverse. First thing, anytime you have a function which has an inverse, you can always identify the graph pretty easily if you have one of those. So for instance, if I have a function let's call that f. Firstly, is that function one-to-one?
Yep.
Yeah.
All right, so if it's one-to-one, it has to have an inverse. Here's the relationship between a function and its inverse on a graph. Namely, a function and its inverse, graphically, are just a reflection across the line y equals x. So if this is my function, well, the inverse, because an inverse is found simply by switching the x and the y coordinates, it's horrible. Well, hopefully you get the idea. I'm not the best artist in the world, but do you get the idea that I'm trying to show you here? It's just a reflection across the line y equals x. If this is a one-to-one function, this also has to be a one-to-one function. If this was not one-to-one, this would not even be a function. That would be a problem. Show of hands feel okay with the idea of the graphs. So a function and its inverse are just reflections across the line y equals x. Secondly, if f is continuous on a certain domain, then f inverse will be continuous on a certain domain. Just keep this in mind. The domain of f becomes the range of f inverse. So I'm going to state this and I'll try to explain a little bit better for you. The wording's a little bit weird, but here I'll say it this way. If f is continuous on a certain domain, this doesn't mean continuous everywhere. This means that where it's continuous, and I'll explain the rest in a minute, where it's continuous, so if f is continuous on a certain domain, f inverse will also be continuous on a certain domain. However, I'll put this in parentheses here. The domain of f inverse is the range of f. So for instance, let's say f is continuous somewhere, okay? It's continuous on a certain domain, which means it's continuous on its range as well. So where a function's continuous, it just doesn't have any holes or gaps. So what this says is that if f is continuous from x equals negative 3 to x equals positive 2, well, it's also continuous on the range from, let's say this is like negative 2 to positive 5. That means f inverse will be continuous from, what did I say, negative 2?
Yes.
Negative 2 to positive 5 along the x-axis. The range of f becomes the domain of f inverse. So you could think about it this way. If f is continuous along a certain range, f inverse will be continuous along that certain domain. Okie dokie? So continuity, it doesn't, try not to think about just a domain or range issue. Continuity just means it's continuous, as in it has no jumps, gaps, holes, asymptotes, or anything like that, right? So what we're trying to say here is that where f is continuous on its range, f inverse is continuous on that particular domain. It's stated a little bit funny. So if f is continuous on a certain domain, f inverse will also be continuous on a certain domain, but this is the range of f. Here, example. Small example, because I can tell by looking in your eyes, some of you are like, what? What are you talking about? Here we go. Easy example. Let's say that here is here's our function. Here's our function. If this is the function f, firstly, is it 1 to 1?
Yeah.
It's got to have an inverse. How you find inverses is you just reverse the x and y. So if this is at -2, 7, we're going to also have a point on the inverse from where, at what, where?
7, -2,
Yeah.
2.
Cool. And if we have a point at -3, 1, where's our point on the inverse going to be?
1, negative.
Okay, my graphs are not to scale, but let's make the points bigger and hopefully you get the idea. So this just flip-flops right across the y equals x line. Well, here's the deal. What we'd say here is this is continuous along the x-axis from -3 to -2 and continuous along the range, so that's our domain, and continuous along the range from 1 to 7. Well, that means here it's continuous along the domain of 1 to 7 and along the range from -3 to -2. Does that make sense? Do you guys see how the range and the domain switches? So don't get all hung up on the continuity. Basically says if this is continuous, that's continuous. That's the idea. Anyway, also in the last thing, thing we'll work most with right now. If f is differentiable, which means we can find a derivative at any point along the domain for which it's defined. If f is differentiable, f inverse is also differentiable.
Can you real quick just mark where those points are at on the graph, like with the box, like number, comma, number, so I can make it better on my notes, because I'll forget it. Like
Go for it. -3, 1, -2, 7.
-3, 1. Okay.
And do the same thing there.
That's -3, 1.
1, -3, 7, -2. So a couple things that we know about the properties here. A function and its inverse have a relationship graphically of just a reflection across the line y equals x. Are you guys okay with that one? Okay. Secondly, basically, if this is continuous, this is continuous. That's the idea. If this is not continuous, this is not continuous at some point. That's the idea, okay? The range of f becomes the domain of f inverse. That's another idea. Also, if f is differentiable, it means we can find a derivative, then f inverse is differentiable. And here's actually how you do it. If I want to find the derivative of an inverse function, here's one way we can do this. Now, if you're wondering, why don't we just find the inverse and take the derivative of that? Sometimes it's not that easy to find an inverse explicitly. Sometimes it's hard to do that. So we have this way of working around it, where all we need to do is find the derivative of the actual function and use that to our advantage to find the derivative of the inverse. And here's how we would, at a certain point, here's how we show it. So if I want to find the derivative of an inverse, I can do it two ways. I can find the derivative of the function first, which would, sorry, the inverse of the function first, then go for the derivative, or I can do this. I can find the derivative of the actual function, compose f inverse into it, which if you don't know how to find that explicitly, you can't do that for every point, but you can do it for a certain number of points, for like a given point. And I'll show you that example in just a minute. So we can actually work around finding the derivative of the actual inverse itself. Let me give you a couple examples on how we can evaluate inverses at certain points given a function. Let me give you another piece of notation here too. Some books do this. Some books say, well, you know what, let's suppose g of x equals f inverse. Then they do this. They say g prime of x, so those of you who like the prime notation like this, g prime of x would then equal 1 over f prime with g of x composed into it. That's the idea. Do you guys see that the notation is it's saying the same thing here? Do you guys see that? Here's derivative of the inverse, here's derivative of the inverse. Remember, that's the inverse here. The derivative is 1 over the derivative of f, no problem, with the inverse composed in it, with the inverse composed onto it. Show of hands if you feel okay with that. Would you like a couple examples? Because right now it's pretty vague.
Yeah.
Okay. Let's start here. Just some basics on how we can go about evaluating the inverse at a certain point without actually finding the inverse. I'll say that again. How we can go about evaluating the inverse at a point without actually finding the inverse. Please pay attention here, because the next part of this, using derivatives, is going to be based on this idea, okay? So, very similar to this idea. So, quick example. Some of your homework questions are worded just like this. So let's suppose we have a function x cubed minus 1, and what our homework or what our test or whatever you're trying to do, this is how it's worded. What I want to do is find f inverse of a when a equals -1. Find f inverse of a when a equals -1. I'm going to give you some steps on how to do this. It's not a hard concept for the most part, but here, just think of this for a second. We're going to use one biconditional statement that's absolute truth for inverses to make this thing work in our advantage. Here's the statement we're going to talk about. F of x equals a if and only if f inverse of a equals what, do you know?
-1.
Not -1, no.
X.
X, that's right. Look. If I plug x into our function, it gives me a, then I should plug in a into my inverse and it'll give me back x. Remember, inverses undo functions. Does that make sense to you? Mm-hmm. So this would have to equal x. So if and only if. If and only if that. Well, then here's what we're going to do. Step 1. Set f of x equal to whatever a you are given. Check this out. If we set f of x equal to whatever a we're given, if I can find out what x is, I know what f inverse of a is. So, set this equal to whatever a you're given. What's our function in this case?
X is very last one.
Good. Let's set that equal to whatever a I'm given. How much is the a? So here on this step we do x cubed minus 1 equals -1. You okay with that? By the way, this is a really simplistic example. You'll see that in a second, but I just want to get you into the pattern of this. Next, solve for x. how would I solve this for x?
Plus 1.
Okay, so we add 1 and then,
Take
what's
the
our
cube
answer
root.
going to be?
0.
So if I solve this for x, sure, add 1, we're going to get x cubed equals 0 or x equals 0. Step number 3, man, we're just going to state what the inverse evaluated at a is. So find f inverse at a. So here's the deal. You guys believe this, yes? His definition for inverses basically says, okay, well, if f of x equals a, then f inverse of a equals x. You switch the x and the y, that's how inverses work. So it's going to undo whatever operation, whatever function you have. Okay, well, we're going to use this. We're going to say, okay, if f of x equals a, then in this case, x cubed minus 1 equals negative 1. If we solve that for x, check this out. If we solve that for x, this is the x we're talking about. So when we set our function equal to a and we solve it for x, we're basically saying, okay, well, if this works in terms of our function, then if I take f inverse of, what's my a again?
0. I mean, negative 1.
Then f inverse of negative 1 has to equal the x that I just solved for. Equals?
0.
That's what we're trying to find. That's the idea. It's kind of working backwards. We set our function equal to a, we solve for x. That x is the answer that you're looking for in this case. Does that make sense to you? It's a little backwards work, it's a little weird. Let's try it one more time, and then we'll move on. This one's take a little bit more thinking, so I want you to really focus on this. I know some of you don't really like trigonometry all that much, but we're going to deal with it right now. Here's our function. So here's our function. I want us to find f inverse of a. So same question. When a equals, what do I want? 1. Okay, why don't you guys tell me, what's the first step? What would I start by doing?
Set f of x equal to a.
Very good. So let's do that. If we set f of x equal to a, and we solve for x, that's our answer. If we can just solve for x. So on our first step, we're going to have what equal to what, please?
3 over pi x plus sine of x equal to 1.
Very good. Notice what I'm not doing. I'm not taking this and plugging it in. That's not the idea. I want to find out when a is plugged into f inverse, what do we get? So I'm not plugging this number in here. I'm setting this equal to a. So 3 over pi x plus sine x equals 1. Now I'm giving you this example to show you that it's not always very simple algebra to solve this. This was really simple algebra. Sometimes you actually really have to think about what's going on here. So there's no algebraic way to solve that. We're going to have to just think about what we can plug in to make this true. What do we put here to make that true? Start thinking. I'll give you a second. So think about it for a second. See if you can find something. Remember, it's got to be the same thing in both spots. So same thing in both spots. Think of the angles that you know sine for. I wouldn't be thinking of like 1/2, because you can't plug in 1/2. I'll be thinking like pi over something for 2 reasons. Firstly, I got to get rid of a pi here. Does that make sense? Got to get rid of a pi, otherwise I'm not going to get a 1. So a pi over something here and a pi over something here, and see what you can get, so that when you add it together, it's going to give you 1. Think for a minute.
Pi over 6.
If you can't think of one off the top of your head, start trying some. Start trying things like pi over 2, or pi over 3, or pi over 4, or pi over 6. Start thinking of them. Let's try pi over 2. If I try pi over 2, what's the sign of pi over 2?
1.
1. Pi over 2 here, pi's would be gone. I'd have 3/2 plus 1. Is 3/2 plus 1 equal to 1?
No.
No. Okay, so pi over 2 doesn't work. Try things like pi over 3. All right, so pi over 3. What's sine of pi over 3?
Root 3 over 2.
Root 3 over 2. Well, there's no way that I'm going to have a root 3 over 2 and something that doesn't have a square root in it and get a 1, so that can't be right. Pi over 4 also has a root 2 over 2, right? So that's not going to work. How about pi over, what do you think?
6.
Pi over 6 might work. Let's try that. So if I do pi over 6, so this would be step number 2. We're showing our work here. How much is sine of pi over 6?
1/2.
What happens here?
1/2.
It's kind of cool, right? We got pi's are gone, 1/2. Does it work? Okay, so here's the idea. We just found out the number so that when I plug it into my function, it gives me 1, my a. So how much is our x equal to in our case?
Pi over 6.
Yeah, our x in our case is pi over 6. Show of hands if you feel okay with that. Now, let's just put it all together. Remember that f inverse of a equals x, whatever x you just found here. So what we'd show this as is f inverse of what? What's our a?
1.
Equals,
Pi over 6.
that's the idea. That's working with inverses. Okay, quick show of hands if you feel okay with the idea of this. I gotta be honest with you, sometimes it's really easy, sometimes it's not. Sometimes it takes a lot of thought here. So, but do you understand the concept of it?
Yeah.
Okay, cool. The last thing we're gonna talk about in our section is how to find the derivative of an inverse evaluated at a point. I think I told you that sometimes it's really easy to find the inverse and just take the derivative of it. Sometimes it's not. So I'm gonna show you a way that we can go around actually finding, like without actually finding the inverse function to find a derivative evaluated at a point. So here's what we're going to do. We're going to start with this example. We're going to find the derivative of g, where g equals f inverse for f of x equals x cubed at the point 2, 8. If you're wondering what in the world are you talking about, Mr. Leonard, this is making no sense to me. Here's the plan. What's a derivative mean, in other words?
The average change,
That's not the average change.
instantaneous.
Change. Or slope of a curve at a point. You ever heard that before? I made my students memorize to say, derivative is slope of a curve at a point. Now said it. So derivative is... Oh, you're getting it! One more time. Derivative is...
Slope of the curve.
Okay, so what I'm looking for is the derivative of... Remember, this is the inverse. The derivative of the inverse, or the slope of the inverse at that point. Are you guys with me on this? So at this point, let's just practice for a second. This point is on the function. On the inverse, would it be 2, 8 or 8, 2? So we'd be finding the slope of this curve, inverse, at 8, 2. Are you all with me on this? That's the idea here. That's what we're going to be doing. I got some steps for you on how to do this every single time. Honestly, it's not that hard. Step number 1, just verify that this point is actually on that function. It's very easy. Just plug it in. So verify that point's actually on the function. So step number 1, f of, what would you plug in? Would you plug in 2? Would you plug in 8? Yeah, plug in 2. Make sure it gives you 8. So f of 2 gives you 2 cubed, gives you 8. That's step number 1. Just verify that the point is on the curve. Because we want to make sure that we're talking about, for our inverse, the same scenario here, only in reverse. So 8, 2 rather than 2, 8. You guys okay with that so far? All right. Number 2. Number 2 is kind of a two-part thing. I want us to find the derivative of the function. So find f prime of x and find g of whatever your y coordinate is. Because when I find my inverse, they're going to switch. So find g of 8. Let's start with the derivative firstly. What's the derivative of f? What are we going to get?
3x squared.
Perfect. How about g of 8? Keep this in mind. I know we're using g, but g really stands for the inverse. If f of x has a point 2, 8 in it, tell me something about the inverse. What happens if I take the inverse? Are you guys okay that that's actually the inverse here? Yes, no? Since this says, okay, that's the inverse. If I say, hey, plug in 8, what's that have to give me?
2.
Yeah, the point says it, okay? The point says when you plug in 2, you're good, 2 to the function, you're going to get out 8. Therefore, the inverse says when I plug in 8, I'm going to get out 2. I don't even care that you have a formula. This says it for you. So that's got to give you 2. Show of hands, feel okay with that one. Okay, now here's the cool part. If we know that, all we got to do is use that formula I just gave you. So our formula said g prime of x gives you 1 over f inverse, f prime evaluated at g of x. Here's what we're going to do. We're not trying to find g prime of x in terms of x, we're trying to find it at an actual point. So we're trying to look for g prime of 8. G prime of 8 says this. It says you take 1 over the derivative of f evaluated at g of 8. Now, how much is g of 8?
2.
So we're going to find, check this out, please watch. We're going to have f prime of, what? How much is g of 8? 2. All you got to do is take that 2, plug it in here, and figure it out. 1 over 3 times 2 squared. How much is that going to give us? 1 over 3 times 2 squared. Yes, no, or did I lose you? I don't want to lose you, but I want to make sure that you're okay on this. We're going to do one more example on how to do this, but I want to make sure that you guys are good to go. So the idea is this. G is going to stand for your inverse. If I want to find the derivative of g at a certain point, here's the way that we can go about it. We don't actually have to find the inverse function of g to do it. What we can do is say, all right, well, cool. Firstly, let's make sure that 2,8 is actually in the function. It is. If 2,8 is in the function, 8,2 is in the inverse function. Not sure if you understand that. Okay. All right, well then, that's all this is saying, is that 8,2 is in the inverse function. All right, cool. Well, let's find the derivative of f. Very easy to do for us because we're in Calculus 2. And then here's how we can find it. If we want g prime of whatever point I'm talking about, g prime of 8, take 1 over the derivative evaluated at that number, whatever that is. So just take the derivative, plug this into it, and that's the slope of this curve, the inverse curve, at the point 8,2. Show of hands if you feel all right with that one. Okay, it's a little weird, right? We're kind of going like the backdoor approach here. We're not going directly at it, we're going around it. Can we do one more example, see if you really hang on to it?
Yeah.
Maybe you can try some of this. So same idea. I want to find the derivative of g at a point for this function. So same start here. Let's just do it when f of x is x squared plus 1 cubed at the point 1, 8. Okay, quickly. First thing we're supposed to do is what, please?
F of x.
Let's verify it. Yeah, plug in the 1, make sure it gives you 8 for the function itself. Doesn't?
I don't think it does. Did you plug in 1?
Plugged in 1.
No, you get. Oh yeah, sorry, you get 2.
Did it work?
Add.
Okay, so if I plug in 1, you get 8? You're good. Okay, listen, you can do the second step right now, at least part of it. Do the second step. Second step is a two-parter. Name one thing you're going to do in the second step. You have to find the derivative because that's what we're using here. So find the derivative. Also, let's do this together right now, okay? I'll have you do the derivative in just a second, but check this out. I know I'm about to find the derivative, but tell me this. How much is g of 8? If you know f of 1 gives you 8, how much is g of 8? How much is that?
1.
Perfect. Tell you what, when you get down to this step right here, after you find the derivative, what number are you going to be plugging in?
1.
It's the same thing you found right there. Just plug in 1. So I want you to find the derivative right now of f. What do we need for that derivative? What are you going to use?
Chain rule.
Love the chain rule. Hopefully you got that. Did you get that? Yes.
Yes.
Okay, cool. Hey, you guys are practically done. Now, we're going to use the formula that I gave you. The formula says if you want to find g prime at whatever this point is, if you want to find g prime of 8, what we're going to do is put 1 over f prime of g of 8. That's the idea. 1 over f prime. How much was, we already talked about this, how much was g of 8 again?
1.
So really, all it says is, okay, make sure this works, firstly. Find the derivative, plug in that number. Plug in that number to your derivative, put it over 1, or put it under 1, and you're basically done. Have you guys plugged in 1 to this? You guys see where to plug in the 1?
Yeah.
To plug in 1 right here, how much did it give you?
24.
24? So we'd say g prime of 8 equals 1 over 24. Here's what it says. Provided that you are actually able to find the inverse of this. If you were to find the inverse, take a derivative, and plug in the number 8, it's going to give you 1 over 24. It's finding the slope of your inverse at 8, 1. That's what it's doing. It's kind of cool, right? Show of hands feel okay with that one. That's it. That's really all we're going to go for as far as inverses. You guys have any questions at all about this so far? Can you find an inverse if I give it to you? Can I find an inverse if I give you a function? Okay. Can you do examples like this one where they're pretty basic?
Yeah.
This one you have to think about. It's a little bit harder. Are you guys okay with these two? Cool. Question?
So for that one where we just have to think about it, will we ever be able to isolate that x in later on? So we just gonna deal with that.
Yeah, you can't. Not here at least. You can't get that explicitly defined. You can't solve it for x.
It's all unit circle pretty much, right?
This one's a thinker because you have an algebraic concept and you have a trigonometric concept. You can use an inverse here, but you're going to be stuck with an x on the side. So, good questions. All right, we're going to move on. The next thing we're going to talk about, because we've already talked about natural log function, it really seems logical that we're going to talk about exponential functions next. Because exponentials and logarithmic functions are hand in hand. They're inverses of each other. Hey, that's what we talked about, inverses. So we did logarithmic, okay. We did inverses. Now we can talk about exponentials because exponentials and logarithms are inverses of one another.